So this lesson will be working with rational functions. So we're going to learn what a rational function is, and we're also going to learn about properties of what we call vertical and horizontal asymptotes. So that's going to be some new vocabulary, vertical and horizontal asymptotes. This lesson will also determine, again, this domain and range. So again, as we've been talking about, we're talking about functions. Remember, a function is when the domain has to go through a series of calculations, and the result is then our range value. Now remember, in some functions, there is x values that you can't put in, and that happens when you have a fraction. And if you notice, a rational function has a numerator and a denominator, so it's going to have probably some domain restrictions. So a rational function basically means you have a polynomial function over top of another polynomial function. So it's a polynomial over a polynomial. So remember, as I said, the denominator cannot equal 0, because remember, when you divide by 0, the answer is undefined. So this is where this domain restriction is going to happen. So it's all about this denominator. That denominator cannot equal 0. So also, as far as getting 0 for the rational function to equal 0, notice that the numerator must equal 0. If that isn't possible, then this actually will be a range restriction. So sometimes it's not possible to make 0 in the range value, and that's when the numerator can't be 0. So we have to pay attention to that as well in working with rational functions, since there's a numerator and denominator. So remember, if you have 1 over 0, that's undefined. But to get 0, it has to be 0 over some number, or 1, if you will. The 0's got to be the numerator. That will give me 0. But remember, if it's not possible to make the numerator 0, then our answer cannot be 0. So let's start with finding the domain. The domain, since we have a rational function, there is going to be a domain restriction, and that's going to be because of the denominator. So to find that domain restriction, what we do is we set the denominator equal to 0. That's going to help us determine the domain restrictions. And these values must be excluded from the domain. In this lesson, we're going to be using the set builder notation. So we're going to be using the set of x's such that, and this is where we insert the inequality inside the set builder notation. So there are several different inequality symbols. We're going to be using the not equal sign quite a bit as well in this lesson. So if I want to find the domain of this rational function, so notice how we have a polynomial over a polynomial. To find the domain, though, since it's got a restriction, we set x minus 5 equal to 0, and we solve for x, and we get x equals 5. So we're not allowed to choose 5 as a domain value. So the way we write the domain, though, is we use the set of x's such that, that's our set builder notation. And what we do is we write x cannot equal 5. So we write this inequality statement inside here. So that means all numbers except 5 are our domain. So the set of x is such that x cannot equal 5. So that means all numbers but 5. So that's a simpler way of writing instead of that interval notation that we've had to deal with. So look at this next polynomial, or I'm sorry, this next rational function. So to find the domain of this function, we have -3 over x squared minus 1. Again, since there's a denominator with a variable in it, we set x squared minus 1 equal to 0. Now, there's actually two ways to solve this. One way is to get the x squared on one side. X squared equals 1. And then what we're allowed to do is we're allowed to take the square root of both sides. In doing so, this becomes x equals plus or minus the square root of 1. And then if we take the square root of 1, we actually get 1. So one of the answers is x equals a positive or a negative 1. Another way to solve this is recognize that this is a difference of squares. So I can actually factor this into x minus 1 times x plus 1, since it's a difference of squares. And if I set each factor equal to 0, I'm going to get x equals 1 here, and I'm going to get x equals -1 for that one. So notice how there are two domain restrictions. So the way we can write this in, then is the set of x's such that x cannot equal 1 or x cannot equal -1. Something like that would be acceptable. So exclude those two values. Okay. So again, in my lab, you may have to look at what they want there for that one. It may be something different. Sometimes they use commas instead of ones. Sometimes you may see them go the set of x's such that x cannot equal 1, comma, -1. So you never know with my lab math on how they do that. So sometimes, say using an or, they may use a comma. So just note that when you work on an example like that, that it's going to be one or the other probably. So if I look at this next example, we have this x squared over x squared plus 1. So if we want to find the domain of, this should have like an r of x here, equals, so this is a rational function. Again, we set the denominator equal to 0. We have this x squared plus 1 is equal to 0. Notice that's not factorable. I could use the quadratic formula to solve this, but actually an easier way to do it is just isolate the x squared. So I have x squared equals this -1. If I take the square root of both sides, that's going to be x equals the plus or minus the square root of -1. And remember, when there's a negative inside the radical, a -1 inside the radical, that gets replaced by an I squared. So remember the imaginary unit I, we said I squared equals this -1. So this really becomes x equals plus or minus the square root of I squared. In other words, this is going to be plus or minus I. Now, right now, our domain, we're talking about real values. And since this is imaginary value, then we're talking no domain restrictions. So there's not any domain restrictions on this one. The domain would be, if I'm using interval notation, it would be -infinity to infinity. If I'm using set builder notation, it could be something like the set of x's such that x is an element of R. Or sometimes in my lab math, they just say the domain is all real numbers. So notice how we have a negative inside of square root. That indicates this imaginary unit, or remember how we talked about that with complex numbers. So this does not have a domain restriction in this one. Even though there was an x on the bottom, when you square a number, there's no way to get a 0 here, because the only way to make the denominator 0 is you would have to make this a -1. -1 plus 1 would be 0, but there's no number that you can square that's going to give you a -1. So this does not have a domain restriction. Something else we need to pay attention to is in determining the domain, this must be done before reducing the rational function. So if I was looking at this problem right here, since it has a denominator, we would have x plus 2 is equal to 0, and we would say x equals -2. So as far as the domain goes, it will be the set of x's such that x cannot equal -2. That would be our domain. Now, keep in mind, this actually does simplify down because the numerator is factorable. That would be x minus 2 times x plus 2 on the top over x plus 2. So notice that the function actually simplifies down to f of x equals x minus 2. But this function does have a domain restriction. I cannot choose -2 for the x value. So we have to do the domain restriction before we do any reducing. So if I want to graph h of x equals 1 over x squared, it's not a bad idea to practice what that looks like with the graphing calculator as well. So if I type in y equals, if I clear this off here, 1 divided by x squared, hit graph. Notice how I got my scatter plot still on. So if I hit the second stat plot, I turn him back off, hit enter, toggle it over to off, hit enter, hit the graph again. Notice my window looks awkward too. So remember, under zoom, if I hit number 6 for standard, that gives me kind of the graph there. So notice how it kind of is a strange looking graph. rational functions will have these strange looking graphs. They have kind of what we call boundaries in them. So one things we talk about as far as in behavior. So as I'm moving to the left, notice that the y values, they're approaching a certain value. They're getting closer and closer to the x-axis. So if I look at the table, as I go here, let me, in my table here, looks like I've got that off too. So above window, I have a table set spot. Right now, my independent variable is on ask, and I need to change my independent variable back to auto, hit enter. If I go back to graph now, there's my graph still, hit my table. Now it generates my table. Notice, there's an error where x is 0, because notice how if you choose 0 for x, that's going to create a 0 in the denominator. That's going to be a domain restriction. So you can kind of see that there just in the table. If I scroll up, as your x's get further and further away from 0, further and further left, notice that your numbers are getting closer and closer to a specific value. They're getting closer and closer to 0. So you kind of see that in a table, that as your x's are going towards negative infinity, your y values are approaching a specific value. They're actually approaching the value 0. Similarly, as I move to the right, as my x's get bigger and bigger and bigger, notice how if I get over on the positive side, the same thing's kind of happening. Notice that as you get closer out, further right, notice that your y values are getting closer and closer to the value of 0. In other words, they're getting closer and closer to the x-axis. So as x is approaching infinity, y is getting closer and closer to 0. The question is, can you get 0 for y? Remember, to get 0 for y, the numerator would have to be 0. That's not going to be possible. So there's no way to get 0 for y either. So your y values will never be 0. So what they're doing is they're getting closer and closer to the x-axis, but they will actually never touch the x-axis. So the x-axis actually becomes a boundary line. Notice the y-axis is also a boundary line. So when you graph this, we kind of see some things going on there. The end behavior, we kind of see this graph is getting closer and closer to the x-axis here, and it's getting closer and closer to the x-axis here. We're kind of seeing that end behavior out there on the far left and the far right. As far as the domain restriction, what we pick up on is, x cannot equal 0, because that's what would make the denominator 0. So what we pick up on as x is approaching this domain restriction, as x is getting closer and closer to this domain restriction, in other words, I'm looking at values that are very, very small. I may have to change my my table. If I changed my settings in my table here, notice that let's change it back to the independent, back to ask. So if I go back to my table, as I approach 0 from the left, so from the left side, as we approach 0, so in other words, let's say I choose 0.1. Oops, get back over here on this side. So if I choose x to be 0.1, notice how y is 100. Notice that, that's getting very large. If I pick a number even closer, if I pick like 0.01, like 100th, that's smaller than 0.1. Notice I get 10,000. So notice this graph, as I get closer and closer to 0, this graph is getting extremely large. So the only value I can kind of see is if I pick 1, I'm going to get 1, 1. Or if I pick -1, I'm going to get 1. If I pick 1, I'm going to get 1. So what this graph is doing, as I cross over to this 1 area, this graph is going to turn off and shoot sharply in the upward direction. Same way over here, as I stay pretty flat along the x-axis. Let me get that going a little bit better. Let's see if I can draw a little bit better. So as we kind of see here, -1, 1 would be a point. 1, 1 would be a point. But notice how the graph, as it veers from this point, the graph is going to get closer and closer to the x-axis. And as I get closer and closer to 0, notice that the y values take off and they start to get really, really close to the x-axis. Same way over here. This graph, as you go past 1, the y values start to flatten out and get really, really close to the x-axis. But once you go closer to 0, the y values shoot off in this direction and get rather large. So they are going towards infinity. So as x approaches 0 from the left, notice that the y values are approaching infinity. They're getting extremely large. Okay. The same way, if I'm approaching 0 from the right, I'm getting the same kind of concept. The y values are getting extremely large. They're approaching infinity. So we kind of see that going on. So if you look at this graph, the domain really only has that one restriction. X cannot equal 0. But if I look at the y values, the range and its restriction, notice this graph does not go below the x-axis. So that means as far as your range goes, your y's have to be greater than 0. So if I'm using set builder notation, I could say the set of y's such that y is greater than 0 would be the range restriction. If I'm doing the domain restriction, I'm picking up on this, the set of x's such that x cannot equal 0 if I'm using set builder notation. But what we start to see with these graphs is there's some boundaries that happen here. Notice this graph does not cross the x-axis or y-axis here. So there aren't any x-intercepts and there's not any y-intercepts. Because to get an x-intercept, what you do is you have to set y equal to 0 and you solve for x, but that problem falls apart. Both of them kind of fall apart. And you can also kind of just see it from the graph. So there's the graph of 1 over x squared. It takes on that look. So one of the things I'm trying to get at with this is when you graph these rational functions, you're going to start to see these boundaries appear where the graph gets closer and closer to these lines or these boundaries, and they're going to cause some restrictions in where the graph can go. So if I want to graph this 1 over x plus 2 squared minus 1, notice it's going to be the same graph, but notice how it's going to be shifted to the left 2 and down 1. So notice how there's a transformation there. This graph shifts left 2 and it shifts down 1. So notice how this boundary gets shifted over 2 to the left. So my boundary line gets shifted over 2 to the left. And a lot of times boundary lines we use dotted lines for those. And this other boundary, which was the x-axis, gets shifted down 1 as well. So I have this other dotted line that goes here. So that point that was at 1, 1, it gets shifted left 2 and down 1. So that point that was at 1, 1 gets shifted left 2 and down, down 1. So let me see here. Where am I at? Can't see that. It's not very easy to see there. So let me make a little bit darker mark there. Okay. So I got this tick mark here and this tick mark here. Okay. So this point that was at 1, 1 is going to go left 2 and down 1. It's going to be now at this spot. And this other point that was at negative 1, 1, so the point that was here is now going to be shifted left 2 and down 1. So it's going to be here. So those are my new points that we see graphed. So I'll get rid of that point there. So notice how this graph now, it's going to be approaching, let me do that in a little bit different color there. So this graph is now going to be approaching this boundary line that's actually now going to be y equals negative 1, that boundary. And it's approaching the x equals -2 boundary. And over here, again, it's the same thing. It's kind of approaching this y equals -1 boundary. And it's approaching this x equals -2 boundary now because of that. So we have these boundary lines going in that create this graph here. So that's what we're going to be moving into in this next lesson is we're going to be drawing these graphs that are going to have these boundary lines. So speaking of boundary lines, let's look at then what we call asymptotes. These asymptotes are what we refer to as the boundary lines. So asymptotes are going to be represented by dashed lines, and the graph is going to approach these, but they will not cross these typically. So there are a few exceptions, but what we're going to deal with, nothing's going to cross. They're just going to approach these boundary lines, but they will never cross these boundary lines. That's what an asymptote is. So types of asymptotes, we have a vertical asymptote, a vertical boundary line. So to find a vertical asymptote, the rational function must be in lowest terms to start with. And then we set the denominator equal to 0 and solve. So notice how I can't really factor the top here. So what we do is we just set the denominator equal to 0. So I have x squared minus 4 is equal to 0. And the easiest way to solve this is just move the 4 to the other side. Take the square to both sides and you get x equals plus or minus 2. So there's two asymptotes, x equals 2. We also have x equals -2. Those are our two vertical asymptotes. So vertical asymptotes, we have to write them in the form of x equals. So they're equations. So there are two equations here for the vertical asymptotes. To find the vertical asymptote of this x function, notice how the numerator is factorable. That's going to be x minus 3 times x plus 3 because that's that difference of squares. On the bottom, for this to be factorable, notice how since the coefficient of x squared is 1, we know we have to have an x and an x in these first positions. But what goes to this last positions are the factors of a -21 that add up to be a 4. So the factors of 21 that come to mind are like a 3 and a 7. Those are factors of 21. And to get a -21, one of them has to be positive, one of them has to be negative. But to get a positive 4, that means the 3 would have to be negative. So -3 times 7 does give me -21. And -3 plus 7 does give me 4. So that becomes my second part of my factorization, x minus 3 and x plus 7. So when I reduce it, though, notice that these x minus 3s will divide out. So my new function now is x plus 3 over x plus 7. So when I find my vertical asymptotes, I just set the denominator equal to 0. So I set x plus 7 equal to 0, and I end up with x equals -7. That's going to be the vertical asymptote. A lot of times we'll use v dot a for vertical asymptote. So that's how we can find vertical asymptotes, is set the denominator equal to 0, but there is a catch. If it's factorable and part of it can be divided out with the factors of the numerator, we have to use the lowest terms version. The next thing we get into is what we call horizontal asymptotes. There's two types of these. Now to find them, what we do is we look at the degrees of the numerator and denominator. So notice how the degree of the numerator is 3 and the degree of the denominator is 5. If the degree of the denominator is larger, our horizontal asymptote is going to be y equals 0. So again, a lot of times we will use HA for horizontal asymptote. So y equals 0 represents the horizontal asymptote. In other words, that's going to be the x-axis. That's going to be the boundary line. The other type is if the degree of the numerator and denominator are the same, use the leading coefficients. This will represent the constant used to describe the horizontal asymptote. So notice how the degree of the top is a 2 and the degree of the bottom is a 2. So since they're the same, what we do is we just use the leading coefficients. So our horizontal asymptote is going to be y equals 8/4. But since that reduces, we would say y equals 2. That's going to be our horizontal asymptote. It's going to be the horizontal line passing through 2. So what I do is I use what's called the leading coefficients. Where it gets tricky is this third example. If the degree of the numerator is 1 more, notice that if the degree of the numerator is 1 more than the denominator, then an oblique, or what we call a slant asymptote, will exist. Long division is used to determine this equation. So notice how the degree of the top is a 4 and the degree of the bottom is a 3. Notice that the degree of the top is 1 more, because if you subtract 4 minus 3, we get that 1, that's 1 more. So this means an oblique or slant asymptote exists. To find it, what we do is we use long division. So to do long division, the x to the third minus the x squared plus the 1 is on the outside. And on the inside, we have this 3x to the fourth. Notice since there's not a x to the third term, I'm going to put like a 0x squared there. And then there is, there's not a cubed term. This could help us kind of keep things lined up a little bit. So I don't have in the numerator, there is not an x cubed term, so I put a 0 as its coefficient. Then you do have a minus x squared, but notice the linear term is missing, the degree 1 term is missing, so its coefficient was a 0. And the constant was missing, so it's also a 0. So when we do long division, we just focus on the front term. We ask, well, how many x to the thirds can I get into 3x to the fourth? And all I really are paying attention to are the exponents. So how many x, if I have 3, what do I need to make 4 of those x's? Well, if I have 3 x's, I need 1 more x to make that x to the fourth. So I just need 1 more x to get an x to the fourth. So x times x to the third becomes then this x to the fourth. We multiply x times negative x squared, that's going to give me negative x to the third. And x times 1 gives me x. So this term's missing. I have 1x here. So this term's missing here. So I could put like plus 0x squared for that. And then at this plus 1x. So remember, when you do long division, you have to subtract. So what I do here is I have to change the signs. So this is going to turn into negative. This is going to turn into a positive. This is going to be a negative. And this is going to be a negative. Those signs have to change. So now I combine like terms. So 3x to the fourth, lose an x to the fourth, gives me 2x to the fourth. I have, actually, I did that wrong. Scratch all that. Back up here. It's been a while since I've done my long division. Get to see mistakes in action. I want that front term to miss. So let's try that again. So to get an x to the third, what I want to do is I want to get this 3x to the fourth here. So what I need is actually a 3 and an x, because 3x times x to the third gives me 3x to the fourth. So I want to match that. So I want to make this the same. So I need the 3 and the x. So 3x times x to the third does give me this 3x to the fourth, because I want this term to go away. So it's going to be a 3x to the fourth. Let me get this little mark out of the way here that's strayed. So then if I multiply 3x times x cubed, that's 3x to the fourth. 3x times negative x squared gives me negative 3x cubed. 3x times 1 gives me 3x. So there's not an x squared term. So I put plus 0x squared. But I do get a positive 3x here. Okay, that looks better. So remember, I do have to subtract. And when I subtract, what we do is we just change the signs and add. So that's a negative, that becomes a positive. This becomes a negative. This becomes a negative. And now I'm going to combine those together. So yeah, the 3x to the fourth, they drop out. So now down to a 3x to the third. I do have a negative x squared comes down. I do have a negative 3x comes down. So now I want to figure out, well, how many x to the third does it take to get this 3x to the third? Well, all I need there is a positive 3. So I put a plus 3 up here. So I multiply the 3 times the x to the third, and that gives me 3x to the third. 3x to the third. 3 times negative x squared gives me negative 3x squared. And 3 times 1 is going to give me 3. So I don't have an x here. That's 0x. And I have now a plus 3 comes down. So remember, we have to subtract. And the way we subtract is we just change the signs. So that becomes a negative. This becomes a positive. This becomes a negative. This becomes a negative. So what I come down with now is 2x squared minus 3x minus 3 comes down. Now notice since this exponent is bigger than this no longer can work. So this becomes my remainder. So this is going to be plus then this 2x squared minus 3x minus 3 over x cubed minus x squared plus 1. So what happens is this part here will drop off, and this part here is going to be used as the slant asymptote. So this part gets negated, and we say our slant asymptote is going to be, so it's going to be y equals, we'll do better than that. So slant asymptote is going to be y equals 3x plus 3. That's going to be our oblique asymptote. So to find the oblique or slant asymptote, we have to actually use some long division, but you got to execute that correctly. So what's happening is this part here, as x is getting very, very large, this is going to turn to 0. That's why we're kind of allowed to drop that out. As we are approaching infinity, this is going to actually drop out of the problem. So we'll talk more about that if we have time. I don't know if we do any of those. So let's see what else we have here. So putting it all together. So in your assignment, you're going to be required to find the domain, the range, x and y intercepts, vertical asymptotes, horizontal asymptotes, oblique, or slanted asymptotes. So domain is, again, you have to go from left to right. So notice how if I go from left to right, there's a left bound here, but notice how as you go to left, this asymptote gets in the way. Our graph starts to bend away from that and go just down. So when you do the domain using interval notation, it's going to be negative infinity, and you are now getting close to this asymptote, which would be 2. So that boundary. So we do not include that boundary, so we have to use a parenthesis in union with, and then this open boundary again, and out to the far right, we're going to have an arrow again. So it's going to be to infinity using interval notation. If I'm using inequalities, we could say x is less than 2, and the other inequality would be x is greater than 2 using inequalities. So that would be the areas where the domain exists. If I'm finding the range we have to use lower bound, upper bound. So notice how if I go down low, I have an arrow, which means negative infinity. But notice how there's this spot here where there's this boundary. That means we have an exclusion. That exclusion happens at this spot right here, which would be a 1. And then if you go from there, notice how up here is another arrow, so it's infinity. So notice how we have 2 intervals. So the range would be considered negative infinity to 1, and you can't include the 1, so it's an open bound, in union with 1 to infinity. If you're using inequalities, you would say y is less than 1, and y would also be greater than 1 using inequalities. And sometimes they'll use a comma to separate those inequalities. The X and Y intercepts, it looks like the only place I see it crossing the X-axis is here. So it looks like the X and Y intercepts are both 0. So if we use ordered pairs, the X-intercept would be 0, 0, and the Y-intercept would be the same thing. It would be 0, 0. It's the same spot. That's the only spot that it crosses the X and Y axis is here. The vertical asymptotes, the vertical boundary is going to be the up and down dash here. So what we're seeing there is 1, 2. Looks like the vertical asymptote is going to be X equals 2. That's that boundary line. The horizontal asymptote is the one going from left to right boundary. And that's going to be the horizontal asymptote is going to be a horizontal line. So it's going to be Y equals 1 as the horizontal asymptote. And also, this does not have any slant asymptotes. So this is going to be none here. So if I look at this graph here, again, if we want to find the domain and range, the domain, again, we're looking from left to right. So notice how there's this arrow here, but notice how there's this boundary line here. And then we have this other right arrow over here. So notice how we have these two intervals. So using interval notation, you could say negative infinity to that boundary, which would be -1 in union with -1 to infinity. If you're using inequalities, you could say I have to be left of -1, so X is less than -1, and you have to be right of -1, so X is greater than -1 if I'm using inequalities. The range, you're going to be using the, you're going to be going lower to upper. So notice if I go low, what I'm seeing is, look, there's this tucked away over here is this little dotted line. The X-axis is the boundary. So you can't go below the X-axis. So Y has to be above 0. And notice how on the other side, we have these arrows. So your range really is going to be from 0 to infinity. Well, in other words, Y is greater than 0 if I'm using inequality notation. The X-intercept, it's where it crosses the X-axis. It doesn't cross the X-axis, so this has a none for that. The Y-intercept is where it crosses the Y-axis, and we see that that is Y equals 2 or 0, 2 if I'm using an ordered pair. The vertical asymptote is the vertical dashed line, and you can kind of see that's going to be X equals -1. The horizontal asymptote was that X-axis, so that's going to be Y equals 0. And again, this does not have a slant asymptote, so this is going to be none. So oblique or slant, none. So looking at this graph here, we have the domain and range to deal with to start with. So domain, we're looking from left to right. So notice how this graph kind of goes left. And I do see this boundary, but it looks like the domain gets confusing here because this is a slanted line. But does it give me, can I get a 0? I don't think I can get a 0 there. So this is where it gets tricky. So what I'm kind of seeing here is this graph actually looks like it's a, there it is right there. There's the little dot line. I can see it now. So my domain restriction, what I'm seeing is the vertical asymptote would be 0. So that would be my only domain restriction would be that. So you could say the set of x's such that x cannot equal 0 if you're using set builder notation. The range, on the other hand, notice how this continues to go up and down. I don't see a horizontal asymptote anywhere. So there's not any range restrictions. So the range is going to be the set of y's such that y is an element of R, or, we can also write all real numbers for that. The x and y intercepts. The x-intercepts looks like there's two, -1, 0, and 1, 0. The y-intercepts, it looks like it doesn't touch the y-axis, it only approaches the y-axis. So the y-intercepts is none because it doesn't touch that. The vertical asymptote would be the y-axis. So that's going to be x equals 0 for that boundary there. X equals 0 represents the equation for the y-axis. The slant asymptote, the horizontal asymptote, there's not one. So none. But there is a oblique asymptote. To find it, it's an equation of a line. And notice that we do know 2 points. We know 0, 0, and this point 1, 2. So remember, to find a slanted line, we can use the equation y equals mx plus b. And I can use those two ordered pairs to find the slope. So it's going to be 0, 0, and 1, 2 are my 2 points. So using my slope formula, it's going to be the change in y would be 2 minus 0 over the change in x, which is going to be 1 minus 0. So that's going to be 2 over 1, which is going to be 2. The y-intercept, or the b, is where it crosses the y-axis, and that slant asymptote does cross the y-axis at 0. So b is going to equal 0. So your slant asymptote is actually going to be y equals 2x plus 0. Or in other words, just y equals 2x would be the oblique asymptote. So we have to use the formulas to find the equation of line. And remember, that's going to be y equals mx plus b. So let's look at another one. So this is fairly busy as well. Starting with the domain, notice that the left bound, we have an arrow, but notice how we have a vertical asymptote here, and we see another vertical asymptote here, and then we see this right arrow. So if I'm going from left to right, the domain is going to be, if I'm using interval notation, it's going to be negative infinity to -2 in union with, then I go from -2 to 2, and then in union with, I go from 2 to infinity if I'm using interval notation. So that's going to be the domain. The range, we look down low to high. Notice that the range, I have a lower bound of an arrow, but notice how it does include, it does touch there, it does touch 0. So one of the intervals is going to be from -infinity to 0. And you would include 0 there. In union with, notice here though, the graph doesn't happen again until you get above this horizontal asymptote, which is going to be located at 1. So it looks like the other part of the range is going to be from 1 to infinity. And 1 would not be included because that vertical asymptote is not being touched. So that'd be my range using interval notation. The x-intercepts, I do see it touch here at 0, 0. So the x-intercept would be 0, 0. The y-intercept, that's the only place I'm seeing it touch the y-axis as well, is at the same spot. So the y-intercept is also 0, 0. The vertical asymptotes, so notice how we have one at x equals -2. We also have one at x equals 2. Those are your vertical asymptotes. So these vertical lines that are dashed are your boundary lines there. The horizontal asymptote is the one that's going from left to right, and notice how that's passing through 1. So y equals 1 would be the horizontal asymptote. And I don't see any slanted asymptotes, so there aren't any oblique asymptotes. So if I want to find the vertical, horizontal, or oblique asymptotes, let's look at these equations here to see if we can identify those. So remember, it's all about the degrees. If the degree of the numerator, since it's 1, and the degree of the denominator is 1, since they're the same, what it is, it's the coefficients of the top and the bottom. So t of x is going to equal this 5 over 1, which is going to turn into, I'm sorry, your asymptote is going to be y equals 5 over 1. So y is going to equal this 5. Notice on this one, notice how the degrees again are the same. So since the degrees are the same, it's just going to be the leading coefficients. So r of x, I'm sorry, writing the, so again, this is going to be a, let me try this again. I need to read my directions a little more carefully. So my directions say find the vertical, horizontal, and or oblique asymptotes. So let's start with the vertical asymptotes. The vertical asymptotes, remember, you have to make sure the function's simplified first. It is set the denominator equal to 0. So I have x plus 4 is equal to 0. So the vertical asymptote is going to equal x equals -4. The horizontal asymptote does exist because the degree of the numerator and the degree of the denominator are the same. So that's going to be y equals 5 over 1. So your horizontal asymptote is going to be y equals 5. And the only way to get an oblique asymptote is the degree of the top has to be bigger than the degree of the bottom by 1. And since they're the same, the oblique asymptote does not exist. It does not have one. So it does have a vertical and a horizontal. So to find a horizontal, to find the vertical, I may have to do some factoring here. The numerator is factorable. And notice that the factors of 5 that give you a 6 would be a +5 and a +1. Now, does the denominator factor? So if I have this 2x squared plus 7x plus 5, so I'm going to do this over here a little bit. So if I set up 2 sets of parentheses, 2x squared only has one possibility, 2x and x. 5 only has one possibility, a 5 and a 1. So I'm going to put the 1 here and the 5 here. And to make it a positive, you need a plus and a plus. For this to work, though, the outer and inner terms have to give you the 7x. So if I do the outer terms, that gives me a 10x. If I do the inner terms, that gives me a 1x. 10x and 1x does not give me 7x, though. So I'm going to scrap that. That possibility doesn't work. So let's move the 5 and 1 and see if that makes a difference. So let's switch the places of the 5 and 1 because that makes another possibility. So if I put the 5 here and the 1 here, if we do that math, the outer terms gives me 2x, the inner terms gives me 5x. That does give me 7x, so that is factorable. So 2x squared plus 7x plus 5 does factor into 2x plus 5 times x plus 1. So what happens is the x plus 1s cancel out. So that's our new function is r of x equals x plus 5 over 2x plus 5. Excuse me. So the vertical asymptote, we set the denominator equal to 0. So 2x plus 5 is equal to 0. We lose the 5. 2x equals -5. Divide by 2. X equals -5/2. So it does have a vertical asymptote. The horizontal asymptote, since the degrees are the same, it does have a horizontal asymptote. And remember, it's just the leading coefficients. So it's going to be y equals 1 over 2. And that would be it. It does not have a slant asymptote because the degrees is not one bigger in the top. So I'd have to have an x squared on the top, and I don't. So in this third example, again, to find the vertical asymptotes, we want to factor, since the top doesn't factor, we know it's not going to simplify any, but we need to go ahead and still factor the bottom. X squared minus 5x minus 14. And we'll go ahead and just set that equal to 0. That's going to be our vertical asymptotes. And since the coefficient x squared is 1, we can just go x in parentheses, x in parentheses. All we got to do now is figure out what are the factors of a 14 that maybe will give me a -5. So from there, the factors of -14 that give me a -5. I'm thinking a 2 and a 7 would give me a 14. To get a -5, though, that 7 would have to be negative. So -2 or 2 times -7 does give me -14. 2 plus -7 does give me a -5. So let's just factor into x plus 2 times x plus 7 is equal to 0. So we've set each one of these equal to 0 and solve for x. So that would be x equals -2. This would equal x equals 7. That would be the two vertical asymptotes. What else do we have to do here? Horizontal asymptote. The horizontal asymptote, since the degree of the bottom is bigger than the degree of the top, that means our horizontal asymptote is going to be y equals 0. Since the degree of the bottom is a 2, the degree of the top is a 0. Remember, there's an x to 0 there. So that means our asymptote is actually going to be y equals 0. And again, there will not be a slant asymptote, since the degree of the top would have to be bigger by 1 than the bottom. So that kind of concludes then our lesson on rational functions involving those asymptotes as well.